Hello, welcome everyone to the PHM seminars initiative from the PHM Society. My name is Nika Lefteroglou. I am an assistant professor in the Department of Aerospace Structures and Materials, and I'm leading the ISP group, Intelligent System Prognostics for Operations and Maintenance. Almost a year ago, during the annual PHM conference in Nashville, while enjoying some good whiskey with my colleagues, Professor Geraldo Rosas and Professor Marcos Orchard, we discussed how great it would be to have more PHM events throughout the year. That conversation planted the seed for what has now grown into the PHM seminars. And today, nearly 1 year later, we are very pleased to officially welcome you to this new initiative. And we would like to thank a lot the PHM board for their support and for giving us the opportunity to launch this series. Their help has been invaluable. So now some more information about the PHM seminars. The PHM seminars will take place quarterly. In each session, experts from academia, industry, and government will share their insights on PHM. All seminars will be live streamed on the PHM Society's YouTube channel and followed by an interactive Q&A session via the YouTube chat box. If you have any questions or feedback related to the PHM seminars, please feel free to reach out to us via the seminar's email address. The structure of the seminars is simple. We will always begin with some announcements, and later on we will introduce the speaker, followed by the seminar itself, and finally some Q&A. For today's announcements, I would like to invite everyone to consider submitting your work to the International Journal of Prognostics and Health Management, the leading online journal for multidisciplinary research on prognostics, diagnostics, and system health management. It's open access and completely free of fees and charges. We also hope to see you at our upcoming conferences. The 17th annual PHM conference, which is going to be in Seattle in October 27th, and later on this year to the Asia Pacific PHM conference in Singapore in December 8th. And now it's my great pleasure and honor to introduce the very first speaker of the PHM seminar series, Dr. Kai Goebel. There are so many things that I could say about Kai's contribution to the PHM field that an hour would hardly be enough. But just to give you a sense about Kai's contribution to PHM, is one of the co-founders of the PHM Society. He has co-authored more than 400 articles on PHM and founded the Prognostic Center of Excellence at NASA. His research journey brought him to various academic, government, and private research institutes, and he received his PhD from UC Berkeley in 1996. The title of his seminar is PHM Unplugged, Past Lessons, Future Frontiers. Dear Kai, The floor is yours.
Thank you, Nick, for your kind introduction, and Geraldo for facilitating this meeting. I'm very honored to be here today and share some of the work that I have done and my insights into PHM. The title of the talk, as you saw, is PHM Unplugged, and what I want to do is give a maybe not quite so formal introduction into the evolution of PHM, touch on a few milestones and breakthroughs, talk about some of the bottlenecks that we still have towards full implementation of PHM, talk about some challenges and then some frontiers in research. So what I'm going to do first is sketch out very roughly the journey of PHM as I see it. These will not be discrete kind of events, but more center of gravity milestones that bleed into other decades as well. But fundamentally, prior to the 1970s, we had mostly reactive maintenance, followed by manual repair. Things were run until they broke. Not that people wanted it, but they didn't know better. And then deal with the downtime in some fashion. From the 70s to 80s, we see a shift slightly towards scheduled maintenance with interval-based fixes. Checklists were used, and the aim was mostly to reduce catastrophic failures. In the 80s, then we started to see more of condition-based maintenance. There were great advances in sensor developments. Oil and vibration analysis was really at the center of much of that, and we see the advent of alerting. In the 90s, that really was the time when PHM as a concept emerged, complete with remaining useful life prediction, and that's also when the guaranteed uptime paradigm ushered in a great renaissance in remote monitoring and diagnostics. The 2000s then saw more of an understanding of the physical failure, also fleet level, remaining useful life prediction, decision support became something that was following prognostics and also optimizing over these decisions. In the following decade, AI, which had been really used throughout of the journey of PHM, really made it into the consciousness of people. Deep learning was a concept that really was touched upon a lot, as well as edge and cloud computing. Now we're looking more at resilient systems, human-machine interaction, distributed and blockchain-enabled PHM, incentivized PHM and quantum computing. What I'm going to do next is fill in those blocks with a little bit more color and looking at PHM from different perspectives. First of all, I want to look at safety, which was really a driving event for what is now PHM. At the end of the 19th century, when we had the second industrial revolution, we saw a uptick in fatalities due to failures of bridges, vessels, boilers, structures, and so on. That was not very popular. So professions banded together to address this by introducing the concept of material testing, and the scientific method took hold. We also looked at guidelines for designing with proper safety margins. That was a concept. Licensing became a requirement. Code of ethics were crafted by the different professional societies, and standardization and codes were embraced by all major professional societies, including ASME, ASCE, IEEE, NSP, and so on. What you see on the right is pictures of various failures. boilers, at the lower right, where steam engines just exploded, as well as you see the bridge that collapsed in the upper right-hand corner, and then in the top right is where another vessel exploded in Boston. It was the big molasses catastrophe. The safety then, moving forward a few decades, was really the ancestor of hump systems in aviation. And what you see here are a few aircraft. The top left is the U-2 spy airplane. This was a high altitude airplane that was introduced in the 50s. And a number of them were shot down over hostile territory. A number of them just simply crashed. And engineers were trying to figure out how to assure the safety of operations with pre-checks, and then trends and machine operations were relayed back to the people on the ground after the flight. In the 60s then, we saw the introduction of magnetic tapes, where vibration mostly was recorded on the engine using pickup of acoustic signals. And these magnetic tapes were then, after the flight, again analyzed by a ground station, played back and compared to a healthy engine on the ground. So that was being done for both the U-2 as well as for the F-104 starfighter, which is the top right image. Many of those actually crashed. It was not a particularly reliable aircraft, but about 110 or so were lost. And again, that really motivated the need for monitoring things. In the 60s, with the A7B, the concept of monitoring those tapes became a routine post-flight check for the Navy. And in the 70s, with the Harrier, they really introduced the vibration data recorders with multi-channel tape recordings, which didn't just log vibration information, but also other relevant parameters like turbine temperature, nozzle position, oil parameters, and so on. And that really marked the first fleet-wide condition-based maintenance program for the Royal Air Force. Then in the 70s and 80s, all that was digitized, and one transitioned from analog magnetic tapes to solid-state digital recorders. And that made it much easier to download and analyze the data. And that was important for the safe operations of these aircraft. Aeronautics wasn't the only domain where safety was important. The space program certainly was very much interested as well. Here, the motivation was in part also to look at how to deal with the launch escape system, which required monitoring of data to make split-level kind of decisions whether to abort or not. And so that then required a more methodical review of the failure history, flight history, corrective actions that need to be done to determine lead times before failure. And there was a push also to formalize what is the risk. Some of the responses were not just the monitoring system itself, but also hardware redundancies, or to design out certain types of problems. The space program then with Apollo really pushed the boundary of that much more. Again, formalizing what are the risk goals is important, so that you have some requirements towards which you can design your system. And as we probably all know, failure mode and effect analysis, which wasn't invented by NASA, but it was really pushed and formalized as an important tool in determining risk and understanding the performance of the system was advanced. And here you go through each portion of the design, determine potential faults and its impact, which then allows the designers to eliminate the fault mode or reduce the likelihood of the events and also to mitigate consequences. So just stopping here for a second, what we have seen now is for safety, there was a need for monitoring, which required condition sensing, which really pushed the development of the data acquisition systems from manual to recording on magnetic tapes to digital systems. Also, sensing was greatly advanced, and the need for warning systems required some analytics of the sensors, which then pushed the development of analytics methods as well as alerting. And the need for establishing design criteria required an understanding of failure modes, which were then encapsulated in different kinds of fault models. Now, safety wasn't the only driver. Another motivation was cost and uptime, mostly in other domains. And here we can go back to the early 20th century, where we see some of these concepts being realized in very mundane kind of applications. On the right, you see a sewage plant, and on the left, you see a power substation. These were sometimes or oftentimes located not necessarily right where people are, maybe for a sewage plant for obvious reasons, but it was important that these were operating. And very early on, some of the sensors might trigger a response, and that was then transmitted via telegraph to operators who could then respond to that by sending out a field engineer and to take care of the problem. Much later, the concept of remote monitoring was advanced, and telegraphs were no longer being used, but telephones were being used. And what we see here is a CT scanner. And in the 80s, then there was a desire to make sure that CT scanners were up or were operating at all times, in particular when they were needed. And GE at the time introduced a program whereby they called in via a modem into the CT scanner to observe the health of the machine. Now, they were, as still is the case, oftentimes not designed with health in mind. Instead, what was being recorded and played back were error codes that software engineers had written mostly for themselves. And these were oftentimes just comments or event logs. And the analysis then revolved around correlating these entries with particular faults that were seen in the field. And at that time, case-based reasoning was used as a technology to solve that problem. If a problem was found, a field engineer was dispatched to prevent downtime or to fix the problem if a fault had already occurred. That worked really so well that the hospitals at the time told GE, well, we don't really need you because our machine seems to be working all the time, which is an interesting anecdote because it also communicates the need to make sure that your customer knows what you're doing for them. In the 90s, then there was a big change in how things were done. The old model was really one of parts and labor, where OEMs and MROs earned revenue based on your system failing, and then they could charge the customer for parts and for labor to repair the thing. That really was there was some misalignment of incentives, because fundamentally it meant that more failures meant more revenue, which was not really in the best interest of the customer. It also meant that airlines and militaries had to carry very large spare inventories, and so there were some obvious disadvantages to that model. GE then also introduced the guaranteed uptime model. So instead of charging for parts replaced, the OEMs sold availability or flight hours, and OEMs would then take responsibility for repairs. The customer only paid for guaranteed engine or aircraft uptime, and the sum of those payments was less than what the customer would have previously paid for parts and labor. It also meant that the risk for failure shifted to the OEM. And now the OEM was no longer interested in failure of their equipment. And that really sparked a huge resurgence of understanding how your system was operating. And it was the dawn of modern remote monitoring. So at that time, GE was monitoring aircraft remotely, mostly via satellite downlink from aircraft in flight. Data bricks were collected once during takeoff, once during climb, and once during cruise. During cruise, fundamentally, the aircraft waited until all the transients had settled, and then a data brick was sent down to a ground station, which then could immediately analyze the data. At that time, in the 90s, GE monitored around 5,000 engines. Each aircraft flew roughly 5 times a day. So you were getting 25,000 flights, and I don't know, 20 or 30 parameters were being recorded. And so suddenly there was a large number of data that could be analyzed and that could no longer be done really manually. And so analytical tools were being developed to understand the data and to alert in an automated fashion. So again, taking quick stock of where we were with this paradigm change, we go from run to failure to guaranteed uptime, and that, as I said, that sparked a renaissance of remote monitoring. Data acquisition was done through any means possible. Satellite is expensive. Other means were also being used for different types of equipment where possible, telephone, radio, etc. And this also saw the birth of real-time analytics, including also prognostics, where you were trying to then trend where data were going and then forecast at what point of time one might see a failure and at what time to perform maintenance. Applications really were extremely broad. I showed aircraft, commercial aircraft, and I also showed an example of a wind turbine, and also of medical equipment. But fundamentally, this concept was being applied to any industrial equipment, whether it was locomotives or anything you can really think of, oil and gas equipment, pipelines, compressors for pipelines, and so forth. And this really meant the transitioning from reliability engineering to PHM, which incorporated proactive strategies, and then we truly went from condition-based maintenance to predictive maintenance. So let's now talk about some of the bottlenecks that we're still seeing. Not all is good. PHM is oftentimes still an afterthought, and that has to do in part with the fact that systems were built many decades ago. Plants might have been built 50 years ago. They're still in operation. And 50 years ago, integration of sensors for health management was really not on the radar screen. So even though plants have thousands of sensors, these are meant for controlling the plant, not for health management. And the sensors that are meant for controls don't really make faults observable, or at least not necessarily observable. So one would have to add sensors to these legacy systems and integrate it into a PHM framework, which might be costly. I personally know of the pain of trying to add sensors to a reactor, which requires a custom sensor mount, which involves a custom design and custom fabrication, and all that is quite painful. There's also the issue of transmitting the data. So you might collect the data in the plant, but how do you get it to the server? You cannot necessarily run many miles of wires. So you may have to deal with edge devices, possibly wireless transmission, which may have its own challenges if you are in a metallic structure and where your signal bounces around like crazy, and you can't get it to your server. There's also the issue of IT protocols. You have to somehow communicate with your server and edge devices. You may have to produce on-premise solutions. You have to deal with firewalls and air gaps. These are all very pragmatic and practical kind of problems that still stand in the way of wide-scale adoption. For new systems, of course, we can overcome that. We need to design systems with PHM in mind, and we need to educate designers who are not necessarily taught much about what PHM can do for them. Another bottleneck, as we all know, is data. Data for training and validation. There are field data. Oftentimes when talking with a customer, we hear that they have tons of data. But when you look at the data, you oftentimes find that they're not the right kind. And what we also frequently see is that there are not sufficiently many run to failure examples. One can build lab testbeds, which are, hard to build. They're expensive. And since we are impatient and we can't necessarily wait 30 years for a bearing to fail, the data are generated under accelerated conditions. And then one has to somehow figure out, how do these accelerated conditions relate to what you might see in the field. Of course, build also simulators. You simulate what you already know. So there are some downsides to that as well. Another bottleneck is still also how do we quantify the benefit of PHM? We want to convince stakeholders to adopt PHM solutions. PHM fundamentally is a business of preventing failure. So it is something that hasn't happened, and a cost not incurred is hard to book in any financial system. And another problem is that your return of investment is oftentimes accrued over a large time frame. So if you have a customer, they look at how much that buys you on an annual basis, but failures may not necessarily happen very frequently, and so you have to wait a long time until you can see that your system works as designed, and where you see a return of investment that becomes positive. We also still struggle how to make promises about the performance of the system, and communicating that to an operations manager is not always easy. It is also oftentimes not easy how to figure out who owns the budget for a PHM implementation. Is it a capital expense? Does it come out of the maintenance budget? Maintenance budgets are oftentimes tight, and so it's tough to get the foot in the door and get things implemented under these kind of circumstances. Next bottleneck is that of algorithms versus software. Algorithms are developed by highly skilled research types, and they look at what they're doing as hit the run button and we're done. These algorithms then need to be transformed onto a PHM platform, which are developed by different people, oftentimes software developers. And the handoff can be complicated. Requirements may not be completely clear, requirements for operations. In operations, there are things that research developers may not necessarily appreciate. What you see here is the need to start, pause, resume after pause, or ignore. And these kind of functions pose complications for your algorithm. If your algorithm is meant to be just run, then pausing it for whatever reason, maybe because you want to do maintenance, or maybe there's an outage or who knows what. Then when you resume operations, you may have to look, then your set point is different, and suddenly you have to process a whole batch of data all at once to catch up with operations. And it's just a little detail that one doesn't think much about during development of algorithms. Also, that of recalibration after maintenance or after partial maintenance is one that requires some thought and some clarity, as well as how do we deal with that. We also, as researchers, oftentimes design our algorithms to some arbitrary performance target. Maybe 5% false positive sounds like a reasonable kind of target, and we can publish many papers on that, but it may not be relevant for your customer. Maybe your customer wants 1%, and maybe the next one wants 0.5%, and the next one wants 0.05%. And so that really means that we ideally have some sort of knob where we can dial in what the performance is without retraining your algorithm each time. Again, something that we're not really thinking much about. Similarly, relating to performance targets is how do we quantify how good your prognostic algorithm is? Conveniently, we oftentimes cite the RMS as a metric, but that may be completely irrelevant to a customer who may not be interested in the cumulative performance of your algorithm. Maybe the customer is only interested of the performance at a specific prognostic horizon, or at a specific time to failure. And so, how do you design your algorithms to these kind of metrics? Sometimes also we like to express our performance using a distribution. And in my personal experience, when I presented the distribution of my prognostics to a customer, they almost fainted because they were really worried that operators would not appreciate the complexity of a distribution. and they didn't really know what to do with the distribution in the first place. They wanted a crisp time at which to take action. And the median or the mean of the distribution might not be the right kind of thing, because they half of the time the component would fail earlier. And I had a customer who wanted the 99.999% percentile, which really means that you have to report on a time that is in the long tail of your distribution. And then you have to figure out how do you quantize your distribution properly. Because if you express that part of the distribution poorly, your results will be equally poor. Scalability is an issue. Bespoke solutions are the norm, mostly because each customer is different. Each set of data is different. The sampling rate is different. The requirements are different. And designing a bespoke solution for a particular system can really only be justified for expensive systems, because that design is also expensive. Moving towards mass deployment, one would really need more generic libraries of fault models and algorithms, which we don't have yet. Similarly, the issue of dealing with customer OT environments is not trivial. There are many proprietary controls environments, and one needs a suite of APIs that can communicate with them all. And you have to figure out whether you want to develop them in-house, buy them, and then also figure out how to maintain them if there are upgrades. Now I want to move to some trends. One trend that we are certainly seeing is the convergence of machine learning and physics models. What we are seeing is that hybrid models will leverage an understandings of physics by either integrating physics into the machine learning models. It could be done explicitly in the model structure, where the connection between nodes could be interpreted as a mass spring damper. And so you build your models or your physics into the machine learning. It could simply be integrated by adding constraints to your objective function. And it could also be done by providing digital twins to augment your field data. Conversely, you could integrate machine learning into physics models, which then would be used to solve optimization problems of models by solving your models, depending on what kind of modeling language you're using. It could also be used to interpolate between operating points, or when data from some sensors are dropping out. And then, of course, you could optimize the entire production process, including the logistics chain in real time, which is a very dynamic kind of problem. Right now, we're looking at the issue of making models more interpretable and communicating the trust that a model is working. This is non-trivial, in particular if you're looking at machine learning models, which traditionally have been looked at as just being black box models. For certain customers who really have to need an insight into why a model comes up with an answer, this is a big issue. And then one needs to balance the accuracy with the transparency and as well as explainability. And that could be important, for example, in safety critical sectors like aviation or healthcare. Another current trend is that of cybersecurity risk in PHM systems. We are seeing an increased risk of cyber attacks And we also see at large, as well as an increased risk of cyber attacks to interconnected PHM systems. So one possible bad side effect of introducing PHM is that you are increasing your attack vector of your system. You make it more vulnerable to attacks because you're possibly integrating with an existing system. You're integrating the IT with an integrated system. You certainly add sensors. You provide access to your system via maintainers or other personnel. And all that means that the overall system, your overall plant might be more vulnerable to cyber attacks. And so we need to deal with strategies to enhance the security in PHM. Of course, the low-hanging fruit is data encryption and secure communications. But then you could also use essentially a PHM system to monitor for cybersecurity events or anomalies in your system and so forth. Another trend that we're observing is that of edge computing and real-time PHM. I touched on that briefly before. Edge computing enables distributed real-time PHM that can operate with minimal latency and greater autonomy. The more data we are collecting, the more bandwidth we will be using in moving that data to a server, which has obvious complications. It also means that one may choose to process some of the data on the edge device and then just send the result to your server. This certainly is an issue in remote environments, if you have a deep sea oil rig or for space exploration, but it really is applicable to many other types of applications as well. And another trend is how to integrate then LLMs locally, maybe also on the edge device. Since LLMs are a hot topic right now, how do we benefit from that? But communicating to all sensors on your system via or with LLM information might be tricky. Speaking of LLMs, I'm sure you're all interested in how we can benefit from this development. Here are a few ways how that might pan out. Again, the most obvious one is that you can use some sort of voice or text-based querying assistant by interacting with your process monitoring system. That's maybe too obvious. What we can do also is to extract knowledge from unstructured data. So you analyze numerical data and unstructured sources, could be sensor comments, could be fault descriptions, operator notes, that provides some contextual support for your decision making. It could be used for virtual assistants for training. One could simulate scenarios and then use your LLM to answer questions from trainees, provide guidance on standard operating procedures and so forth. And that really could be quite a rich application of LLMs in PHM. Could be used for safety compliance. Your LLM could analyze system configurations, maintenance logs, safety reports, and make sure that your processes are compliant with safety regulations and standards. For all of those, obviously, you would have to augment the standard LLM with some application-specific information. Could also be custom maintenance advice. So based on the health status of the asset, as well as the expertise of a maintainer, one could compile a custom maintenance plan, and that could be a very rich application as well. How can we benefit as developers? Well, I'm pretty sure that many of you have already tried LLMs to help with code generation. It might generate code snippets or entire algorithms. It could be functions, data processing pipelines, common ML algorithms. It could deploy models into a production environment. So the painful piece for us, at least, in getting it into production is to create those APIs. Your LLM could just create that REST API for real-time predictions. That would be helpful. It could also develop dashboards using tools like Grafana or Power BI to visualize results. Be used for debugging and error resolution. Is if there's an issue with the model's performance, the LLM could assist you in trying to understand what the problem is, troubleshoot it and the LLM could suggest potential causes or solutions. For example, if your model is underfitting, it could offer a solution like adjusting the learning rate or changing the regularization method or whatever. Could be used for data cleaning. We all have to scrub data that we get, and LLMs really could assist in the pre-processing task, either by suggesting the best approaches for data cleaning. You could just pump all the raw data into LLM and let it figure out what needs to be done. Normalize data, handle missing values, correct formatting problems, and so forth. Or the LLM might just do it by itself. You upload a scrappy data set and out pops a corrected one. LLMs could be used for feature engineering. It could propose feature engineering strategies, transforming time series into meaningful features. It could be used for data visualization. It could either generate or recommend the best type of visualization for the data that you have, or it could generate the code to do that. It could be used for documentation and knowledge sharing. It could be used for writing research papers. It could be used in assisting in summarizing research papers of existing literature. It could rephrase unclear sections if you're reading a paper and you don't know what the author means. It might do that. Or it could also generate documentation or comments for code, algorithms, models, and so forth. All right, enough of LLMs. Let's quickly talk about a few other frontiers in research. One is that of resilient operations. This is where your autonomous system makes proactive decisions about operational strategies to avoid failures in the first place. One would then record resilience scores, monitor those, and take action based on changes to that score. You could also predict or forecast your resilience score. But you also need to make sure that it is adaptable to future technological changes, such as introduction of 5G or other kinds of things. It could be used, for example, in a smart grid where your system will respond to some stress to the grid by adjusting load distributions. It could be another future frontier might be introducing blockchain into PHM. This is a little bit more of an esoteric kind of example where you might use diagnostic prognostics, which helps with efficiency and life extension by proxy. That means carbon avoidance. You could then use verifiable blockchain records and get some credits or rewards for that, which might be incentive to do more PHM and has better climate outcomes. So your verified PHM-enabled carbon savings could be tokenized and generate credit tradable on carbon markets. Let me move a little faster here through the rest. Another frontier would be that of quantum computing in PHM. Quantum computing is coming. It will or could revolutionize the way PHM system handle large data sets and complex simulations or complex plans. So we might move towards solving the elusive, computing the elusive system health of a large complex system, just because your quantum computer will be able to process data in a way that traditional computers cannot, and deal with incredibly complex failure scenarios. Another frontier might be that of changing the role of PHM from remaining useful life prediction of failures to time to event. So we're moving from strictly a degradation kind of environment towards one where that is more integrated with reliability, efficiency of operations, and so forth. And so as a consequence, we would have to figure out how do you build models for an evolving kind of event, which is a richer environment than just an evolving failure. Another future frontier might be that of PHM in human-machine collaborations. Some of that we talked about already when we talked about LLMs, but it really means that we evolve towards making machines from a passive observer to a participant. And so there is a human-machine symbiosis where humans contribute strategic insights and the machines can handle routine monitoring. And PHM ensures that both remain at peak performance. So system becomes self-optimizing. You leverage human insight where automation falls short. And the interfaces are your favorite devices, whether it's AR glasses, tablet dashboards, wearable devices, and whatever else. And then we have applications that come from megatrends. So these are more now applications that we are seeing, mega urbanization. How can PHM help in that? Aging population. How can PHM help with that? Disease and treatment, high-end medical equipment, but also the treatment of diseases. Food has been identified as something that we need to watch. Food supply, sustainable agriculture, water scarcity. What role can PHM play in that? And then, of course, climate change. What can PHM do for energy usage, carbon capture, and so on. So let me stop here just with a few remarks. What we saw was how PHM evolved from a fixed after failure to schedule-based to condition-based to predictive and integrated and an intelligent system. Each of those milestones implied that you need more data, you need more predictive capabilities, you need more and higher system-level integration and closer alignment with human operators. Technology has been supporting all of those steps. And so let me just finish by saying that the future of PHM is not just about machines, but also about humans, sustainability, cognition, and creating a fully adaptive socio-technical systems. With that, I hand it back to Nick and Geraldo.
Great. Thank you very much, Kai, for the presentation. I would now like to open the floor for questions. Please feel free to share them via the YouTube chat. As I see, we have already one question in the chat, which is about how we can address the challenge of obtaining ground truth data in industrial applications.
Yeah, that's a very good question. That is something that we always and traditionally have struggled with. The question really is what is it that is meaningful to you? What is the problem? So if you have a bearing, for example, what is the ground truth of failure of a bearing for you? Certainly we know when the bearing completely falls apart, but we are in the business of describing the health as the bearing is degrading, and so you have to figure out, okay, something about the default mode itself. And default mode in bearings oftentimes is that of spalling. So, spalling fundamentally is like little pit holes in the race of your bearing or the balls of your bearing. And the size of these spalls can be related to the health of your equipment. Now, measuring that is tricky because you would typically either have to do some bore scoping or you would have to disassemble the bearing, measure the spall, and then put it back together. So you can't afford that, obviously, in operations. You can only afford to do that in a controlled kind of environment. And so that is very tedious. But once you have done it, you correlate essentially the size of your spall with the vibration signature that you have. In some other cases, the ground truth may be something completely different, right? It might be, I don't know, if you have corrosion or something like that, it could be the size of your corrosion. But it could also be a multi-dimensional kind of construct where you're measuring different kinds of things. At any rate, getting ground truth is always hard. It is rarely easy. And some work, oftentimes some lab work is required to drill down to what it is that you measure. Now, again, it is important to understand, what is it that you're after. Ground truth could also be, it might not be the root cause of your problem. It might be some intermediate step, and you might just get away with an easier measurement that is more indirect. But one has to be careful because the accuracy of your measurements might degrade then as well. But yep, it's a tough thing. There is no free lunch here.
Great, thank you, Kai. We have another question about how do we expose PHM thinking and systems methods to the general asset management community? What's your opinion about that?
Yeah. So the general asset management community unfortunately doesn't know enough about PHM. And this goes more into education. It goes more into how do we expose or make it known of what we can do. It's more of a PR kind of thing. How do we reach out to that community, right? So do we need to go to their conferences and talk with stakeholders there? Do we need to publish in trade magazines to introduce PHM to the greater asset management community? So this is a less technical kind of problem, but one obviously that is just as important.
And a bit related to that, since inherently in prognostics we have a certainty, we try to predict the future. So by definition, the remaining useful life it's a random variable. So my question is, how do you see that is the most appropriate way to communicate a certainty? Because you also made an example before with the 99.99 percentile, which by definition it's a really difficult prediction since it's in the tail of your distribution. But
yeah, it really depends on what your customer understands. Your customer may not understand that the concept of a probability distribution. And in the example that I cited, that customer advised us not to report the fact that this is part of a larger distribution where there is a plurality of different kinds of outcomes. They defined in that example again, the requirement, and And we then designed a solution that satisfied that requirement. It was at that point, or better, that we were reporting the result, and that satisfied their need. But in other circumstances, your customer may have a different understanding of what certainty means or uncertainty, and you will have to adapt your solution towards the customer's understanding, which maybe work, right? Because I mean, we have our favorite way to express certainty or uncertainty, but that may not be what the customer wants.
Great. And one last question is about, would you say fleet-wide airspace issue prediction would have to be more machine learning based than physics based, as physics based models for airspace operations are limited?
Yeah, good question. So our desire to use a particular method may not match the need of a community for a particular solution. If your customer needs certain insights into how a solution was provided, then you will have to deal with that. How you do that is up to you. If you can do it with machine learning models, that's fine. But it is not appropriate to push a method onto a customer and saying, you'll just have to deal with it. It is for us to figure out how to design a system to the specs of the customer. And I don't think that the customer is averse, towards how we solve the problem. Just that the problem has to be solved, and if it means that there is explainability of your approach, then you have to solve that. If you can do that with machine learning, that's fine. But it's not the question of can we use machine learning in aerospace or not. It's really, can you solve the problem that the customer has? And if you can do it with machine learning, that's good.
Thank you very much, Sky, for all the insights. Unfortunately, we don't have more time for questions. So once again, thanks a lot. And thank you all for watching. And we look forward to seeing you in person in Seattle soon, end of October. And of course, at our next PHM seminar. Have a great week all and see you soon.
Thanks for having me.